Hey guys, let's look at this one from 1985, number 2 from 1985. So it says a 2 kilogram block initially hangs at rest at the end of a 1 meter, two 1 meter strings of negligible mass as shown in the diagram left above. A .003 kilogram bullet moving horizontally with a speed of 1,000 meters per second strikes the block and becomes embedded in it. After the collision, the bullet block combination swings upward but does not rotate. So it doesn't twist like this at all. It just goes straight like that. So calculate the speed of the bullet block combination just after the collision. Collision, your key word here. Collision always means conservation of momentum. So we know that our momentum beforehand of our system is equal to our momentum afterwards. Beforehand, we only have one object moving. I'll call the bullet object 1 and the block object 2. So beforehand, we have the mass of object 1, the bullet, times the velocity of object 1. And afterwards, they're going to have one combined mass. So that's the mass of object 1 plus the mass of object 2 times some velocity afterwards there. So now let's start to plug in some numbers. By the way, this is a perfectly inelastic collision since one becomes embedded in the other. So let's plug these numbers in here. The mass of the bullet is 0.003 kilograms, and it's going 1,000 meters per second, and that will equal afterwards their combined mass to 0.003 kilograms times some unknown velocity. So to solve for this one, all we have to do is multiply 0.003 times 1,000. That will actually just give us 3 is equal to 2.003 times the unknown velocity, and then just divide each side by 2.003. So it's basically 3 divided by 2. So it's basically, if you round off, 1.5 meters per second there. So next part here, it says calculate the ratio of the initial kinetic energy of the bullet to the kinetic energy of the bullet block combination immediately after the collision. So the bullet to the bullet block. So up here, that is 1/2 the kinetic energy mass of the bullet times the velocity of the bullet squared. That will be the bullet's kinetic energy. And beneath that, we'll put the bullet block system, so their combined mass and the velocity afterwards squared. So now let's plug in for these numbers. By the way, the halves can cancel. We can get rid of those. The mass of the bullet is 0.003 kilograms. Its speed was 1,000. Don't forget to square it. And then underneath there, our mass was 2.003, and our velocity was 1.5. Don't forget to square it there. And you will wind up with basically 3,000 over 4.50675. And so when you get those two out there, you will get 666% roughly rounded off. Now, I actually think the way they phrase this question is a little unlike they typically do in this one. Normally, they'll do it flip, so the ratio of the energy afterwards to the ratio of the energy before. So if we flipped that and did 4.50675 divided by 3,000, then we'd only get 0.1%. And the reason I bring that up is that this shows that this is a perfectly inelastic collision, which means it is going to lose energy. In fact, it's only got 0.1% left of its original energy there. Finally, it says calculate the maximum height above the initial rest position achieved by the bullet block system. So this is going to be a conservation of energy problem. So kinetic energy is going to turn into gravitational potential energy. So let's write generically the equation for these. 1/2 mv squared is equal to mgh. Our masses will cancel out here, and so our height then will simply be v squared over 2g. So now we just need to plug in for our values there. This is our velocity, by the way, after they've collided, once they've begun to swing up. So that should be 1.5 squared, and that's 2 times 10, and so you'll get 0.1125 meters, so about 11 centimeters it will swing up there.